Morning, everyone. So yesterday we started looking at isomers. That prefix iso stands for something is the same about the molecules. All the isomers we're going to look at will have the same molecular formula, the same number of each atom, but being isomers of each other, what's different about them? Last day we did structural isomerism. Basically, I would actually physically break some bonds and reattach, try to change out the arrangement of atoms. We saw that different structural isomers end up with different names. So I just want you to start there. We're going to do a quick practice question with drawing structural isomers. Today we're going to learn two other types of isomerism under the category of stereoisomerism. So just for practice, what I'm asking is I want you to draw and name all the structural isomers. So all the different ways things can be bonded. I'm going to do a fairly small molecule. We see as you get longer, you're going to get way more isomers here. So we're going to say C3H6O. All right. So as you're trying this question out, so far I have given you the alkane has a general formula CnH2n plus 2. So one good way of just thinking about this here is just identifying, do we have single bonds, do we have rings and whatnot? In this case here, if I have 3 carbons, if everything were all just single bonds, everything were just saturated, I would have expected 2 times 3 plus 2, I would have expected 8. You'll notice that I'm actually down by 2 hydrogens. That later on is actually going to be called 1 degree. It would have been C3H8 like this. This is actually 1 degree of hydrogen deficiency. So we lost 2 hydrogens, or we have a index of hydrogen deficiency, more on that later on. And pretty much whenever you have that 1 degree, the only way for you to actually have lost 2 hydrogens, either you've ended up forming a ring compound here. If you imagine starting off from propane, just as an example, propane here we have C3H8 like we did. For carbons to end up forming a ring, you actually realize, wait, we actually need to ditch 2 of the arms that used to be holding hydrogens. I lose my terminal hydrogens, and I need to recombine the 2 carbons together to form that attachment. So every ring you form, you end up losing 2 hydrogens. That's 1 degree of unsaturation. Same word here as sort of unsaturated fats. You can either have a ring, or you can either have a multiple bond. If you convert from a single bond to a double bond, you lose 2 hydrogens. Converting a double bond to triple bond, you lose another 2 hydrogens. So that just gives me a hint to what could this molecule look like. Notice that a cyclic compound here is not a structural isomer with the non-cyclic form. The straight chain one here would have been C3H8. I would have had to lose 2 hydrogens, no longer the same formula, so therefore not a structural isomer. So let's start off with the ring. Well, if I have 3 carbons in a ring here, it looks like there's only one type of isomer here in terms of structural isomers. So every carbon has the equivalent of 4 bonds, so they're actually holding, there's our 6 H's. But we also have an oxygen involved here, so let's add an oxygen somewhere. When they ask you to draw a name, they're actually trying to help you out here, because we know different structural isomers will have different names. Either the numbers are different, or the parent is different, something like that. If you draw something and it ends up having the same name, you basically have drawn the exact same structure. Okay. So in terms of the ring here, we're going to actually have cyclo for the ring compound. You might want to emphasize position number 1, but usually chemists will leave that out. Cyclo 1 propanol, and the OH here is the alcohol ending OL. Could I put the OH anywhere else? Could I put it on the top? Well, then I would just rename this one here to be 1. So in terms of the ring compound, you could even call it hydroxycyclopropane, but this one here is the more common name. Okay. So that's the one here that actually involves an OH functionality. What if, for me to actually lose my 2 hydrogens, instead of a ring, what if I actually had a multiple bond? Because I only have 1 multiple bond, I actually only have 1 double bond. So let's take 3 carbons in a row. Instead of having all 8 hydrogens, let's pretend to have ditched 2 hydrogens so that we actually have an alkene. So right now here I'm prop 1ene. We also need to have an OH, an O group somewhere. So the OH could be anywhere. So let's see where I can put on the OH. Let's try to do it as systematically as I can. So my parent is 3 carbons in a row. So my parent is going to be prop 1ene. I have a double bond that starts from position number 1. And I'm going to name this alcohol group here as a hydroxy group. So I can have 1 hydroxy, prop 1ene, where else could the OH go? The OH here could be on position number 2, so I could have 2 hydroxy, or even I could have 3 hydroxy. So those are already 3 different isomers because there's actually a couple different positions. Could the double bond be on the other side? Well, let's try it on the other side. So C, a single bond like this. Well, if we were on the other side here, I'd actually start naming the parent 1, 2, 3 again. This is actually just a duplicate from earlier, right? So far I have the cyclic as an isomer. I have the position 1, hydroxy 1 as an isomer. I have the 2 hydroxy, 3 hydroxy. So far I have 4 isomers. This one here is a little bit sneaky. There actually is yet another functional group that also has this degree of unsaturation. We said we need a multiple bond, but it doesn't need to be a multiple bond between carbons. What if it was a multiple bond with oxygen instead? So what if I had 3 carbons? Instead of the double bond being mid-chain, let's do a double bond to oxygen here. Let's double check that the number of hydrogens is still good. So there we go. Like we said, we only have 1 degree of unsaturation. This time it's just double bond to oxygen. Which family are we in? This part here would actually be shorthanded a CHO group. This is actually an aldehyde functionality. So this one here can be called propanal. Right? Aldehydes is always terminal, so you don't need propane 1-al. Okay. It could also be, what's the group called when it comes mid-chain? We can have 1, 2, 3. Right. Let's double check that we have the same number of hydrogens here. Right. And there we go. Good. C3H6O. This one here would be called, it's in the ketone family, so this is called propanone. And the position is position 2, so propane 2-one. So this is a slightly scary compound, right? I kept it fairly small, so I don't have that many things to play around with. But this formula can actually give rise to at least these 4 different families. You're an alcohol group, you're an alcohol with alkene functionality. Alkene functionality at ENE as the ending. You can be an aldehyde group or you can be a ketone group. If you have a different name, you are a different isomer. Okay. So make sure you do some practice with those structural isomers. Today we're going to take a look at a different type of isomers. These ones here, unfortunately, are a little bit more challenging because they actually need us to actually picture things in 3D. But we'll take this slow here. Stereoisomer. Again, something is different about their spatial arrangement. Something is different about their 3D structure. So stereoisomerism can be further divided into 2 categories. Again, in the past, they used to call this cis-trans EZ. They used to call these ones here geometric isomers. They're trying to phase out this language of this word here, geometric isomer, in place of just calling it cis-trans or EZ, as we're going to talk about, or optical isomerism here, which later on is going to be called RS. We'll do that towards the end of this lesson. Both of these have a different configuration. They have a different 3D structure. They have a different 3D orientation. Now, 3D orientation can work its way in 2 different ways. You can have what's called a conformational isomer. Let me just give you a feel of what a conformational isomer would be. Let's take a pentane. We had done a sort of zigzag-like structure. That is one conformation that pentane can be in. What if pentane, as this long chain here, what if it sort of wrapped in on itself here, not breaking any bonds, but what if I had the 5 carbons almost forming like a ring-like structure here? I haven't done anything. These are not different structural isomers. These are just straight pentane like that, but these are called different conformers. This conformer has everything all in one row. This conformer, this orientation, has the carbons sort of wrapped in on itself. Nothing has changed, so they're not structural isomers, and yet something is different about the 3D picture. The types of isomers that we're going to talk about are not just, oh, it just happened to wrap itself around differently or twist itself differently, you're looking at it from a different side. They are physically different because they actually involve pi bonding, and we're going to see 2 types of this. So without further ado here, let's take a look at cis-trans isomerism. Cis-trans is actually fairly limited. We're going to prefer the more generic EZ isomerism. So these are both under the category of stereoisomerism, both under the category of configurational isomerism. Okay. What we want to remind ourselves here is anytime you have a single bond, single bonds allow for free rotation. They allow for free twisting. Because if you remember here for a single bond, usually the single bond is the stronger of the 2. Usually a single bond is along the internuclear axis. Usually that one there is a sigma bond. Right? A sigma bond here, although these carbons here might hold other attachments here, because it's just a one sigma bond here, this bond here would twist no problem. We can switch to different orientations. Let's say I have a fluorine on the bottom. I can twist that fluorine up top without actually breaking any bonds. It's a different story when we start getting double bonds or triple bonds. For double bonds and triple bonds, we say they're sort of fixed. They don't allow for free rotation. The reason for that, let's take ethene as an example. Whenever you have a double bond, sure, one of them is a sigma bond. One of them is supposed to allow for free rotation. But if you remember from our bonding chapter, our other bond is actually weaker. It's actually a pi bond from unhybridized p orbitals. Those ones there were actually parallel overlap here. The above and below overlap is just one pi bond. Anytime you intend to actually twist these carbons here, you actually physically need to break that pi bond. So because that doesn't naturally happen, especially for an alkene that has one double bond here, you actually give rise to two different types of geometric isomers called cis and trans. So as an example here, let's consider 2-butene. So butene means we have a 4-carbon chain. At position 2, that stretches over a double bond at position number 3. Let me just draw this out here. We can draw this out two ways. C, double bond C. We can have the CH3 on one side, the H on one side here, this CH3 here on the same side, or I can draw it C, CH3 and H, C, H, and CH3. Okay. Let's compare it to the structural isomers and stuff that we did earlier. So structural isomers are things that have the same molecular formula. Yep, that we do. It's the same molecule. Structural isomers actually have, you broke apart single bonds and you reattached it here. No, this time everything is attached to exactly the same things. I have a carbon-carbon double bonded. The carbon is each holding a methyl and a hydrogen, methyl hydrogen, methyl hydrogen, methyl hydrogen. These are definitely not structural isomers. But they are different though. Because this double bond here is rigid, this one here does not allow for free rotation. Because of that double bond, if you end up twisting that, you actually need to physically break a bond. If the CH3 groups happen to be on the same side, that's actually physically different from the CH3s actually being on different sides. So way back, we would actually just call these ones with a prefix. If your isomers happen to have the same group on both pointing up or both pointing down, we refer to that as the cis isomer. If they are actually across from each other, we borrow from the math here. We call it the trans isomer. Trans actually comes right at the beginning of the name. Because the double bond here is rigid, depending on which way this molecule ended up forming, we either have them on cis, so same side, or we have trans, as we have opposite sides. Okay. Notice the name hasn't changed. The name is still, a 4-carbon chain is still butene. We focus in on the carbons that are involved with the double bond. That's where it doesn't twist easily. All the other single bonds would twist no problem. And we look whether the carbons involved in the double bond, are they holding the same group? Oh yeah, both of them are holding a methyl group. If they're the same side, cis. If they're opposite side, trans. Let's look at another example here. We have 3-hexene. So we have 6 carbons in a row. Starting from position 3 over to position 4, we start having a double bond. We want to focus in only on the 2 carbons involved in the double bond. That's the part that doesn't twist. We can have, well, what else are they holding? This carbon is sort of like holding an ethyl group. The other attachment that I don't show you here is actually hydrogen. This one here is similarly holding an ethyl group, holding a hydrogen. If the hydrogens happen to be on the same side, cis. If I happen to draw this slightly differently, sorry, I just skipped over there. If I draw this slightly differently, so draw the 6 carbons in a row again, we have a double bond that doesn't allow for free rotation. What if the hydrogens, one was actually on the bottom and one was actually on the top? All the bonding is the same. We are not structural isomers. But looking at the 3D configuration, if the hydrogens are actually on different sides, we actually now have the trans isomer, and this word here, trans, comes right at the beginning of the name. So I call it cis 3-hexene or trans 3-hexene. These are geometrical isomers of each other. Okay. Let's try out another one here. We have 2-butene. So 4 carbons in a row. Again, we're only focusing on the carbons involved in the double bond because that's the part that doesn't twist. These carbon groups here, even if they just had hydrogen, I already have cis or trans, but now they also put on chlorine groups, 1 on 2, 1 on 3. If the chlorines are on the same side, we would call it cis 2,3-dichloro-2-butene. If instead I had this chlorine here on the opposite side, I call it trans 2,3-dichloro-2-butene. Right? Now what we're going to want to do here, the reason why even cis-trans language is being phased out, cis-trans is a little bit too restrictive. It only works if the carbons involved in the double bond, they're both holding a similar group. What if we have the following situations? What if the carbons involved in the double bond, where it doesn't twist, what if we hold all different groups, right? I have bromine, chlorine, fluorine, iodine like this, right? So these carbons here are not, this one's holding a bromine, this one's also holding bromine, same side or opposite side, right? We can't do that. They're actually four totally different ones. But we still want to be able to identify, is it the same side or is it the opposite side? We're going to phase out cis-trans language and we're going to try to switch it up for EZ language, right? And I'm going to just emphasize how we're going to do this. It's less important to me that the carbon groups actually hold the similar groups. What I'm going to actually assign is some priority based on this Kahn-Ingold-Prelog priority. And it's super simple. What you're going to do is, as you're focused on those two carbons involved in the double bond, you're just going to identify which one has the higher atomic number. Okay. So as you take a look at the atomic number for bromine and chlorine, bromine is atomic number 35, chlorine is atomic number 17. So bromine is the higher atomic number. This one here takes priority. That's the more important group. How about between iodine and fluorine? Fluorine has atomic number 9. The other one, iodine, atomic number 53. That one there, higher priority group here, is the one that has the higher atomic number. So this is an important note to you. Also important for the RS stuff we do later on. So higher atomic number, the higher priority. And now what we're going to do is we're going to say, if the high priority groups are across from each other, we're going to call this the Z isomer. Z is actually German for, the E isomer. E is actually German for entgegen. Entgegen actually means opposites. If they happen to be on the same side, if the bromine and the iodine are pointed, they're both pointing up or they're both pointing down, this is actually the Z isomer. That's called Zusammen, so that's the same side. All right? So we're using this practice of cis and trans. Are the groups pointed the same way or are they pointed opposite each other? But now we're actually, by assigning priority, by assigning which one here is the higher atomic number, we can see, are the high priority groups here across from each other? So it's going to be E, the high priority group here, or are the high priority groups here on the same side? That's going to be the Z isomer. Now, every now and then, sometimes you have a similar looking, let's say I have a carbon double bond like this. Let's say we have H's, right? So I do already have H as already low priority. But what if we have one that's like, we have CH3 and we have CH2, CH3? Evidently here, you would just compare sort of carbon against hydrogen. Well, carbon is atomic number 6, hydrogen is atomic number 1. So therefore, high priority group here, no trouble. That's going to be the trans isomer. But what if I had subbed on here, what if this one here were also an ethyl group? Oh no, they actually now both have a carbon. What you're going to do, if you can't decide at this spot, what you're going to decide is the next spot. So this had a one carbon, this one here had one carbon, the next one out, well, the next one out would just be a hydrogen. This one here still has a carbon. Longer chains would typically have higher priority than shorter chains. And again, as you flip over to the backside here, if those high priority groups here, we number them number 1 here. If they happen to be on the same side, we call it the Z isomer. Z for Zusammen, together. Usually we say this really corny acronym here. Z is on the same side. Right? Just so that you can recognize Z is pointed the same way, right? Very often, cis is going to be Z, but there are exceptions where sometimes cis is actually the E isomer. So it's best just to go directly to E and Z. It's a little bit more general than cis and trans. If those two high priority groups are opposite each other, if they're on a transverse, they're across from each other, they're actually the E isomer. E stands for entgegen, and entgegen here actually means opposite side, and that's actually different sides. Right? So let's see if we can practice this here. Between bromine and chlorine, we had decided bromine is a high priority. Iodine and fluorine, iodine is high priority here. Because they're on opposite sides, this is the E isomer. Again, bromine and iodine, because they're pointed on the same side, this is now the Z isomer. And remember, this lettering here comes before. So if I were to name this one here, we're still a 2-carbon parent, so it's going to be ethane. It just has a few different substituents here. We need to alphabetize them. Let's go start off with bromo here. Let's say 1 and 2. So let's go. This is 1 bromo, 1 chloro. We have 2 fluoro, 2 iodo. all of that is often ethane. And all I'm doing here is, because we are an alkene, because we have that double bond that doesn't twist, we're going to add an E in front of it. E, 1 bromo, da, 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 or Z, da, 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 da. Okay? So double bonds always don't allow for twisting. We always give rise to either cis-trans isomerism or EZ isomerism. So let's just practice here. Focusing in on the carbons involved in the double bond. You look at what each carbon is bonded to. This carbon is bonded to a C group and an O group. Which one has higher atomic number? Well, O does. Let's point that way. The other one here has a C group and a C group. I can't decide at the first position. The next one out would have been a hydrogen. Well, the next one out is a carbon. So this group here is now more important. The more important groups are pointed in the same orientation. So this one here is going to be Z, same side. This one here is actually what I was mentioning before. We have our cis isomer. Cis meant similar group. So both of them are holding a methyl group here. You could also refer to the cis isomer. Cis is usually Z, but usually we just try to phase out cis at all, just in favor of Z. Let's take a look at the next one just for practice. So looking at the carbons involved in the double bond, the longer chain is a higher priority group. This one here, they both have a carbon chain. This carbon, let me just draw it out, CH2 like this, then it's bonded to an O and an H. This carbon is bonded to an O as the next atom. This carbon here is actually bonded to a C double bond O and an OH. I would argue here bonding to two O's is higher priority than just bonding to one O. So the high priority group here is on the same side, so this one here is also Z. Okay, so just take note, from our previous cis-trans sort of language, we're actually going to change it over to EZ isomerism. Now this sort of isomerism here, which is, are they pointed the same way or are they pointed opposite ways, they actually apply to cyclic compounds as well, ring compounds. Cyclic compounds, once the ring forms, depending on what groups are actually on the same side or opposite sides, we had done, as an example earlier, we had done cyclopropane. If you imagine here, let's take our cyclopropane, it ends up forming a nice flat ring like this. If I end up putting substituents on there, if I put on, let's say, a fluorine group, if the fluorine groups happen to be on the same side, right? So you can imagine here's the plane of the ring, right? That's going to be just a flat structure here. If the fluorines are actually on the same side, you can still refer to this one here as cis, maybe 1,2-difluoro cyclopropane, right? Or if it was the opposite way, so if the ring, again, the ring's orientation, right? The ring is just a flat piece of paper. Depending on the substituents, if one substituent is up and the other substituent is down, that's actually going to be sort of across the ring itself. This one here will be known as the trans of that isomer. It doesn't even need to be side by side. So let's say I have a cyclobutane instead. So what if I have a 4 carbon ring? So I have 4 carbon in a ring. The ring sort of makes for me a flat piece of paper, a flat plane. If I have one group here as an F and the other group here as an I, but that's below the ring, that's still the trans isomer. They don't necessarily have to be just one beside the other. Okay, so just watch out for that here. Cyclic compounds also demonstrate this EZ isomerism. This time it's the ring. The ring doesn't twist. Okay. Earlier it was the double bond, right? I would need to break a pi bond. In this case here, the ring forms a flat plane. Am I pointing the same way or am I pointing an opposite way? Okay. That is one type of stereoisomer, one type of configuration isomer. We're going to switch gears now and we're going to change over to our last type of isomerism called an optical isomer. Let me just actually finish up this page for you before we do that. Whether it's cis-trans or whether it's EZ, they can have different physical characteristics. Let's use 1,2-dichloroethene as an example. So we are still ethene. We're still a 2-carbon parent. On position 1 and 2, we subbed on a chlorine. I can have a chlorine group on the same side. So this one here would be the cis isomer. If I do the high priority groups here, chlorine has a way higher atomic number than hydrogen. They're pointed the same way, so this is going to be the Z isomer. Let's compare this to the trans form. Again, it's not a structural isomer. Everything is even attached in the same way, but it's just that the high priority groups are actually pointed opposite ways. This is now the trans isomer. And this is the E. And at least one property we can do right away. Let's talk polarity. So I know C and H here, they have very similar electronegativity, so they're going to be really similar. but this time both polarities are sort of pointed towards this side of the molecule. This molecule here would be a polar compound, while for the trans isomer here, because they're actually across from each other, those dipoles end up canceling out. We actually have a nonpolar compound. That gives rise to a bunch of different properties here. Something that's polar would have dipole-dipole forces. Something that's nonpolar only has London forces. So if you look at melting point, boiling point here, this one has a sort of moderate or medium boiling point, whereas the other one is actually going to have a low boiling point. So that's a physical characteristics, exactly the same molecule, exactly the same attachment, but one polar, not the other one. Usually chemical properties are going to be the same because chemical properties depend on your functionalities. Oh, both of them are an alkyl halide. Both of them have a halogen substituent here. I'll let you look up here. Look up the structure. Usually when we talk about hydrogen bonding, we talk about intermolecular between molecules. When I have a large molecule like this, sometimes the hydrogen bonding can actually be intramolecular, and that actually gives rise to some interesting properties, chemically speaking, for this as well. Let me make one last comment before we look at another type of isomerism. Even a triple bond doesn't rotate. So a triple bond here, that also doesn't twist. This one here would have been one of these is a sigma, two of them are pi bonds. But the reason why we don't have cis-trans, we actually have a nice linear orientation here. So it's always going to be straight across no matter how I twist it anyways. So there's going to be no EZ for a alkyne. Right? Let's end off this lesson here with another type of isomer. This one, unfortunately, is even harder than the EZ. So just give yourself some time just to practice through here. This last type of isomer, also in the past called a geometric isomer. Nowadays, we prefer just calling them optical isomers because they interact with light differently. We can call an enantiomer. An enantiomer is another word for they are perfect mirror images of each other. So this is important. When a carbon atom is attached to 4 different groups, it gives rise to 2 possible enantiomers, 2 possible optical isomers. We're going to call this carbon here. This carbon is a chiral center if it contains 4 different attachments. An analogy for you here, if you look at your left hand and right hand, they're pretty much identical. You have 5 fingers on each hand, but they're mirror images of each other. You can't somehow twist your left hand to actually match up to your right hand. They're mirror images of each other. So what we have is we have a chiral center. We have a carbon that has 4 different attachments. Anytime you have this, there's going to be a left-hand way of orienting this. There's going to be a right-hand way of orienting this. You'll notice that they started using these wedges and dash notations here. I want you to just pretend that this one here is a mirror picture. So I have a chlorine to the right. Now I have a chlorine to the left. This one's pointing up. This one's pointing left. This one here is pointing out of the page, is still out of the page, into the page, into the page. Just like your left hand and right hand, these ones here cannot be overlapped. They look identical, but they're actually a different arrangement. So some other names for this here, we can call it a chiral center. You can call it a asymmetric center. Right. There's going to be some sort of asymmetry to it. You can even call it a stereo center, and really only if you have 4 different substituents. Okay. Here's where it gets really messy. We'll take our time going through this here. Stereoisomers can either be defined as R or S. R actually comes from the Latin. Rectus actually stands for to the right or clockwise, and then S actually stands for sinister. Sinister actually means left. Okay, so here's what we're going to do. Here's our steps. You're going to do that same Kahn-Ingold-Prelog priority pretty much around a chiral center, around a carbon center. Look at the elements that are immediately attached and assign them. Who is the highest atomic number, then the next lowest, and the next lowest, and the next lowest. Okay. So let me just do this one here just for practice. So here, we have a chiral center because this carbon is attached to 4 different neighbors. Let's assign our priorities first. So who has the highest atomic number? Bromine. That's position 1. Then comes chlorine, position number 2. Then comes fluorine, position number 3. Then comes hydrogen, position number 4. Once you assign those priorities here, what I want you to do is I want you to pretend to push the lowest priority group here away from you. Make sure it's the dash. Make sure it's sort of jumping into the page. Perfect. This one here is already into the page. My eye is sort of in front here. I'm sort of looking at it head on. When that H group here is behind the scenes, I want to see for the priorities 1, 2, and 3, do they end up following a clockwise direction or do they end up following a counterclockwise direction? So we have the H away from us. The bromine is jumping off the page here. Priority 1, 2, 3 end up making a counterclockwise orientation. Counterclockwise here is to the left. It's sinister. This is actually the S form. It's the S isomer. Okay. So it's going to take a little while for you to actually look at these tetrahedral structures here, but let's just practice. Let's do this one here. Again, another chiral center. First thing we do is always assign the priorities. So bromine, highest atomic number, then oxygen, then carbon, then hydrogen. Again, they've been nice to you. They've already pushed the hydrogen here, the lowest priority group here, away from us. So now let's see what happens to the 1, 2, 3. The one that's to the right, it's going to sort of go to the one that's jumping in front of the page, and then it's going to go up this way. Notice that one there's a clockwise orientation. Clockwise is actually the R isomer. And just like E and Z, this RS comes right at the beginning of the name. Okay, so R hyphen, whatever the rest of the name is, or S hyphen. It gets a little bit harder. Let's do one more here. Let's assign the numbers. Oxygen has the highest atomic number. That's the highest priority. I have 2 carbon grouping. Longer chains here have a carbon and then a carbon. So that's always higher priority than a shorter chain. Hydrogen is always a low priority group. Sometimes we don't even have hydrogen. But once you assign those priorities, don't do the clockwise counterclockwise just yet. Make sure you've oriented the lowest priority group so that it's pointing away from you. So this one is actually not the drawing that I want. I have the hydrogen jumping out at the page. I want you to pretend you're actually standing on the far side of the molecule and looking at it this way. That way the hydrogen here will be behind the page. You'll need to sort of flip this around here. Normally what we do is we use our left hand and right hand. We're going to point our thumb in position 1, position 2 for second digit, third digit here. In this case here, our wrist is actually going to be the hydrogen. The wrist is actually pointing out of the page at you. Imagine staring at this molecule here from the opposite side. See if you can picture for yourself here. The 1, 2, 3 are actually in a counterclockwise orientation. This one here is actually the S isomer. At first, you could be like, wait a second, how come, like, isn't it clockwise, right? I'm going up and to the right. Remember, we have it looking at it from the wrong side. The hydrogen is sort of jumping off the page. You need to pretend to be standing on the opposite side, looking at it sort of from the back end here, and you'll see that the 1, 2, and 3 are actually in the counterclockwise orientation. So way harder than EZ. It's not just, oh, same side or opposite side. This one, we have 4 priorities to look at. We want to make sure that the lowest priority group is away from us, and then we just identify clockwise or counterclockwise. We'll get some more practice with this in tomorrow's lesson as well. Okay. I just want to finish off this section here. If we have optical isomers, if we have these enantiomers here, what is one physical characteristics that might be different between them? For optical isomers here, they have a special property that they can actually rotate what's referred to as plane polarized light. For light is actually it's actually like a spiraling wave here. What's ending up happening is actually we have electromagnetic waves that are oscillating sort of up and down, so in the vertical axis. We have magnetic fields that are actually oscillating in the in and out axis. That actually gives rise to this sort of spiral orientation. I don't want to study light like this. That's way too complicated. What I'm going to do is I'm going to stick a filter. Usually that filter here is called a polarimeter. And what the polarimeter is going to do is it's going to let light through only in a certain orientation. So instead of doing this sort of spiraling, really complicated electromagnetic field kind of wave here, we're just going to send in light that actually comes in just with one orientation. Maybe just vertically polarized. So, draw this here. So light starts off here as spiraling. We put it through a vertical polarizing filter, so only light having a vertical orientation. It's still oscillating back and forth. It's still going up and down like this. And what we're going to do is we're going to send this light into our chamber. This is where the chemical is. If the chemical is not optically active, it'll do nothing to this light. So if it was vertical coming in, it's still going to be vertical going out this way. Okay, no change. What we're going to do here, we can actually write this down. There is no rotation to plane polarized light. So it was vertical going in. There's nothing in here that's RS that can actually twist it, so it's just going to stay vertical. What if it was optically active? So again, let's take our incident light here. It comes in as a spiral. We put in our vertical polarizing filter. If I put in, let's say, just the R-type compound, okay? This R-type compound here, internally, it already is clockwise orientation. But what it's going to do here is actually going to be able to interact with this vertically polarized light and actually manage to actually twist this light here as it comes through here. I don't know if I'm going to be able to draw it well enough here. It's going to twist it to some degree so that if you have your eye and you're looking head on, you would have imagined that vertical plane polarized light here should come to you vertically like this. Because it's traveling through a length of sample that is optically active, that actually is going to twist it. This black plane here is actually vertical. And what's going to happen is the R type is going to slowly twist this one here. You're going to be down by some sort of theta. The R type is going to twist it one way. And the S type, if I swapped in instead of R, do the other mirror image of it, the S type is actually going to start twisting it the opposite orientation. So that's one really neat property. Chemically, it behaves the same. Physically, it's the same as well. But what's going to happen is it's going to rotate plane polarized light in different fashions. Depending on the concentration of the RS, that's going to have some impact on how much it starts deviating away. But we can actually figure out from this deviation whether it's optically active or not. Now, there's one sort of downside as we just practice this. Substances that rotate plane polarized light, like these optical isomers, like these RNS, these ones here are said to be optically active because they can actually interact with light. Let's compare the optical activity of butane 2O to propane 2O. So first thing we're going to do is we're going to draw them out. Butane 2O, but means 4. At position 2, there's an alcohol group. At position 4, there's an OH group. The rest of these are assumed to be hydrogens. Propane 2O here has carbon, carbon, carbon. Position 2, there's an OH group. Okay, one of these are going to be optically active, one of them are not. What we need for optical activity, like we said, was R and S. R and S will only happen if you have a stereocenter, if you have an asymmetric, a chiral carbon, and that's only a carbon bonded to 4 different attachments. I know carbon single bonds are always going to hold 4 things, but they actually have to be all different. So, not this carbon is holding 3 same hydrogens, this carbon is holding 2 hydrogens. We're focusing on the carbon here. Well, what's going to happen? This carbon is holding on to a methyl group. CH3 is one group. It's holding on to a hydrogen. That's another group. And OH is another group. It's holding an ethyl. This is 4 different groups. That makes this carbon here optically active. It's asymmetric. I'm going to draw this for you in more detail here. But let's compare to the propane tool. Do I actually have any chiral carbons? Well, not the carbons on the ends. Both of these ones here end up holding 3 hydrogens. What about this one in the middle? I'm holding a hydroxyl group. I'm holding a hydrogen group. But I'm holding 2 similar groups here. Because I have, these are both methyl groups. This is not going to be a chiral carbon. So, not a chiral. Chiral is this name for optically active. Not a chiral carbon. So, not optically active. Okay, so let's just draw it out here. I need to draw it with the wedge and the dash to show you whether it's clockwise or counterclockwise. So let's just randomly pick one. So let's take carbon. Let's say the OH is up this way. Let's say the methyl is actually behind the page. There's a wedge that's jumping off the page. And then the other side here, C2H5. Usually I'm going to focus on the chiral center. This is the carbon that's bonded to 4 different things. I wouldn't bother drawing, oh, then it's a carbon and a carbon, because I want to focus just on the chiral center. Okay, let's assign our priorities. We're going to identify here for these elements. Oxygen is the highest priority, then the longest chain, then the methyl group, then the hydrogen. Unfortunately, again, I've drawn it that the hydrogen is actually jumping off the page at me. So what I need to imagine here is imagine standing behind this molecule and imagine looking at it backwards. As you look at it backwards, you're actually going to see going from 1 to 2 to 3, this one here is actually, so far as I've drawn it, counterclockwise. Again, you could say, wait a second, isn't that clockwise? It's because I'm looking at it from the wrong side. The lowest priority group is actually jumping towards me. I want you to actually physically walk around to the other side. You should be able to then see the OH, the C2H5, and the one that's jumping out towards me. Those are actually counterclockwise. Counterclockwise is sinister, so that's actually the S isomer. What about the mirror image? If I put a mirror image to this one here, I would draw a carbon, we would have C2H5, I would have a OH group, I still had the dash back to a methyl group, I have the wedge, that's the hydrogen group. The priorities are still the same, oxygen, the ethyl group, then the methyl group. Again, we have the problem, we're looking at this from the wrong side. So physically walk to the other side, imagine you're staring at it from the opposite side here. As you look at it that way, you're going to find that the 1, 2, and 3 are actually clockwise. And the clockwise is actually going to be the R isomer. So back to our picture here, if in my sample I just put R, it's going to rotate plane polarized light. This is me looking on it. I had expected the vertical just to come straight through, just be undeviated. The R is going to twist things one way, the S is going to twist things the other way. This is actually where in biology they end up getting D sugars and L sugars. That also refers to which way it twists. So these ones here are mirror images of each other. The relationship between these two are referred to as enantiomers. Enantiomers are perfect mirror images. And what you're going to find here is anytime you swap two of them, you've actually created the enantiomer. Okay? So we have an R, we have S. If they are individually in the samples, they are optically active. Both of them are. But what they want to show you here is there is one very special case that this optically active, this RS thing, this thing here is actually optically inactive. It is possible, the one case, let's say in my sample, what if I have a 50-50 mix of R and S? So both R, let's say R is able to twist it counterclockwise, let's say S is able to twist it clockwise. If I have 50-50 mix, part of it is going to twist it in one direction. The other part twists it in the opposite fashion here. They're going to actually cancel each other out so that vertically plane polarized light will just cut straight through and it will be undeviated as well. We're going to give that a very special name. We're going to call this one here a racemic mixture. Racemic mixture. Or you can call it a racemate. A racemic mixture has an equal concentration of R and S. So the twists cancel out. One twisted it clockwise, one twisted it counterclockwise. It's not always R clockwise or S counterclockwise, but one twist, it cancels out the other one. So the twists cancel, and thus it is optically inactive. So even though I had the possibility to twist it, in fact, both of them twist it, but both of them twist it by the same amount. So that way it sort of cancels out. So this one here was definitely the harder of the geometric isomers. There's some questions for you to practice. We'll pick it up from here tomorrow. See if you can start visualizing these things in 3D. Assign the high priority groups and assign whether they're R or S. Okay? Let me know if you have any questions. Thanks, guys.